Hello, I'm Jared Skeens, and welcome to the Zoom room. Today I'd like to cover Pure Math 1 Functions, Part 6, Combined Transformations. In Part 5, we looked at transformations, but one at a time, the three different types. Today we're going to get into the combined, where you're dealing with two at the same time, and so it brings out a little bit more things that we need to pay attention to. And I mentioned this actually in part 5, but I didn't really diagram it for you. I kind of verbally mentioned that there's this kind of three-way thing that you need to be looking for. So I thought I'd diagram it for you to help you visualize it a little bit better, and maybe it'll give that mental image so that as you get into these problems, it gives you kind of a starting point. So basically, these problems can come from three different directions. You've got the function, which is like the equation itself. And you're going to have some sort of a reference or implied starting point. Now, for the sake of our examples, I'm going to use the quadratic as our parent function in the examples. Now, in part 5, I used a couple of different functions, and you should be aware that, or sometimes they don't even give you the equation, they just actually use f of x to represent any function, okay? So your starting function could actually not be a parent function. It might be an already developed function, which then you translate further. Okay, so there's a lot of different ways that this can happen. So here I represented it in basic function notation. For our purposes in this video, I'm going to use this parent function, the quadratic, to illustrate all of this. So you've got your starting function, and then you're going to have after the transformations. And now we're talking about combined transformations. So that means after two transformations, this is going to be the end product. So they might give you both of these, or they might actually only give you one. If they give you both, you should be able to give the descriptions. That is, how is the new function derived from the old function? And you're going to do that through the things that we looked at in part 5. Translation, we'll use this column vector notation. Reflection will be over the x or y axis, and your stretch will be either a horizontal or vertical stretch with a scale factor indicated. So these are the things that you will use to describe the transformations from the original function to the new function. You should also be able to provide a sketch. Now, sometimes, especially if it's not a basic parent function, maybe they come up with some zigzaggy sketch that's kind of like a piecewise function to start with, and then they want you to transform it following the description. That would be this way, from the description here. Or graph it from looking at the functions to the graph. And your graphs can also have an old, meaning your original, and the new, that is after the transformations. Or they give you, say, the equation or the function of one graph. They show the graph moved to a different location and maybe widened or narrowed, and then you have to come up with the description, or you have to come up with the function. So this is a three-way mixture of different ways of handling or dealing with understanding functions and transformations. Okay, so we've already covered this in part 5. Now we want to look at how the combinations can occur. So in what I have, because this is listed as number 4, what I have is part A here. You can have one horizontal and one vertical function. If you have one horizontal and you have one vertical, then the order in which you do them does not matter. So that's pretty safe. However, if you have two, let's start with the two vertical. If you have two vertical combinations, remember the vertical is with respect to the y variable. Your y variable is vertical, okay? So if you're solving for y, whatever your function is, you're going to follow those operations in order of operations. So you follow the order of operations if you happen to have two vertical transformations. So in other words, if you have a multiply, which would be like from a stretch, and you have a translation, which would be an add or subtract, you're going to do the multiply first, and then you're going to do the add or subtract. However, if you have two horizontal transformations, which means it relates to the x variable, well, if you're solving for the x, then that means you have to undo all the different things that are attached to the x. And if you're undoing those operations, it means you're going to go in the opposite of the order of operations. So again, if you have a multiply and an add or subtract, you're going to do the add or subtract first, the translation first, then you will do the multiply, or it even could be a divide if your scale factor is a fraction. Okay, so this is going to be important. Now, the way they state it is that if you have two horizontal or two vertical, it might impact the outcome, the order in which you do it. Well, that's not really comforting for you as a student, or actually, honestly, even for me as a teacher, because when we look at two transformations, whatever piece that we're looking at here, whether it's the functions, the graph, or the description, how are we supposed to know whether or not those two transformations are going to conflict or not, whether it will work or not? So it's better for us if we just follow this advice. That way we know it will work. But it doesn't mean that it can't work if you got them out of order, but it means there is that potential that it does not work out the way it's supposed to. And you can verify these things by looking at specific points in your outcome and double checking it with the function to see if those points are actually agreeing with your function. So there are ways of double checking it after you've done it. But from the beginning of the problem, I don't know, they don't really explain an easy way to determine if it will affect it or not. So we're going to stick to the instructions. We're going to stick to the recommendation so that we're safe. Okay, so let's get started, and I will set up our first example. Okay, here's our first example. Our first example is going to be one horizontal and one vertical. And notice in this case, we are starting with the functions, and the function isn't actually given to us as like a parent function or an actual equation. It's just given to us as an f of x. Now, one of the things I didn't really mention yet that I think will be very helpful for you. I did mention there's the old and the new, the original, and then the product of the transformation. To help me keep track of that, I label everything with these subscripts. So they might not provide the subscripts for you. They just might put y equals f of x and y equals 3 times the function of a negative x. I put in the subscripts to help me keep track of original function or the old function with the new function. And if you remember in part 5, I had here at the top, look at the new function from the old function, okay? So this will help us because we can use a little bit of algebraic representation to help us, you know, connect the important pieces of information here. So what we want in this particular question here is to describe, okay, that was this part of the triangle over here. We're starting with functions and we want to describe. And of course, since we're dealing with combined, we have 2 transformations that we need to come up with. And since it's one horizontal and one vertical, we don't have to worry about the particular order. In other words, we don't have to say, do this one first, then this one, okay? So the order doesn't matter. But what we can do to help us is pay attention to our subscripts. And just in case you might not be aware, subscripts have no mathematical value. They are simply to designate, this is our first equation, this is our second. This is our first x, that's our second x. So there's no mathematical operation involved. So it just helps us to distinguish the two. What we want to do is we want to look at the new one in terms of the old one. So let's start with the x's. We see here that we have a negative x that replaced, and it's our new one, replaced the old one. So you can think of equals as an equation, but also think of it as it replaced it going from the original into the transformation. So if we solve for the new one, in other words, how do we get the new one from the old one? So our new one is a negative of the old one. Well, what does a negative mean? Well, the negative had to do with our reflection, the negative on the variable. And since it's on the x, we're going to call this a horizontal. Don't forget to use horizontal and vertical, and sometimes it can be implied by what else you say, but you do want to keep in mind that all of these have a horizontal and a vertical aspect. So there's 2 aspects to each of these. Translation, the top number is your horizontal, the bottom is your vertical. The reflection is going to be a negative. Well, a negative on the x is a reflection over the y. And if you're reflecting over the y-axis, that's horizontal. If the negative is on the y, you're reflecting over the x. That's a vertical reflection. Same thing with a stretch. You either stretch it horizontally or you stretch it vertically. So make sure that you're using proper terminology. So here we have a negative on the x, meaning it's going to flip over the y-axis. So this is a horizontal reflection over the y-axis. Okay, that's our first description for that particular part. The second part has to do with this 3 in the front. So our y2, and you should reckon, how do we know there's one vertical and one horizontal? Well, the negative is on the x. That's your horizontal one. The 3 is not on the x. It's outside the function. If something is outside the function, it's connected to the y. It's vertical. So this one's horizontal, this one's vertical. So again, we start with the new in respect to the old. It's 3 times our function of x got replaced by that one. So it's 3 times the old one. And it's already in terms of new compared to old. So the only thing that we need to identify this as is it is a vertical, because it's connected to the y-axis, stretch with a scale factor of 3. In other words, everything, all your points get multiplied by 3, and that's going to stretch your graph upwards. So here we didn't have to deal with graphs, but we did have to go from function to description, and we used just a little bit of algebra comparing the new to the old, and it can help you line it up right so that you correctly identify your transformation. Okay, so the one horizontal and one vertical is not too difficult, but let me set up a different example. Okay, here we go. Before we start on this one, I believe that the last example that I just gave you came from the specimen paper. So remember, the transformations part of the functions unit is new to the syllabus in this new syllabus cycle. And so since there haven't been past papers yet, I don't actually have access to, what exactly Cambridge is going to do with these question types. But between the specimen paper and the book, if you happen to be following along in the Cambridge approved book, that previous example was the specimen paper. But specimen papers only give you a very small glimpse of all the possible ways that they can handle a question. So it's it helps, but also we need to make sure we explore all the possibilities. This question actually comes from the book or the curriculum that I use to teach from. And I noticed that in this particular question that they give as an example in the book, I wasn't really satisfied with the way they answered it in their own book. And they actually give 2 descriptions of this, and the question does ask for 2. I'm just going to focus on one. And the first one that they give does follow their advice, but I don't feel it's very intuitive. And the second description that they say, you could give this or you could give, doesn't follow their advice. It happened to work, but you as a student have no idea that it might work if you don't follow the advice. So I don't like the fact that they didn't follow their own advice, and I prefer something that's a little bit more intuitive as far as coming up with our description. So I'll give you the description that I would give if I were looking at this. You don't necessarily have to agree that you like mine better, but if you're following along in the book and you happen to see this particular problem, you can investigate it yourself. But for description here, the blue one, it represents the original. Notice this one is just called g of x, and usually g is the second one. This one would be the f of x, although they don't call it that. And remember, I put in my subscripts so that it helps me keep track of the first and the second. So I'm going to put in my little subscripts there. I'm not sure if you can see that very well in the picture, but I put little subscripts there, okay? So what we want to do is we want to come up with a description, and our description is describing the transformation. Now, what like I said, I don't like the one the book gave that does not follow their advice. I think that's dangerous for you as a student because you can't discern if it will work or not. So we want to follow the advice. For the one that does follow their advice, they jump all the way to 4, and then cut it in half. Well, how are you supposed to know that it's supposed to go to 4? I suppose you can do a little figuring it out to get that, but I think the more intuitive way is just to move it from here to 2. So if we move our graph over to 2, then our first description would be a transformation that follows, or sorry, a translation that follows 2, 0. In other words, everything is moved over 2 units. So if we move our graph over 2 units, obviously our vertex is now in the right place, and that's an important starting point. To me, that's a more intuitive connection that you can visually see. So if I move this over 2, it would be right here, and if I move this one over 2, it would be right here, and if I move this one over 2, it would be out here, and this one over 2 would be right there. So I'm just going to put this in dotted. That would be the first transformation. Okay. Now, what I did was just a horizontal transformation. So by the fact that I said that they didn't follow their own advice, I'm implying that this was either a 2 horizontal or a 2 vertical situation. In this case, the way I'm answering the description, it's a 2 horizontal one. And remember, you go in the opposite order, which means we would do the add or subtract first. Okay, so we do the add or subtract first. We moved everything over 2 units. And actually, the way the book answered it was through a 2 horizontal transformation answer. It didn't ask for 2 horizontal. It just says, describe the 2 transformations. They answered it as a 2 horizontal, but they did the scale factor before they did, or for one of their options, they did the scale factor before they did the translation, which is not the opposite order. So we actually don't have to do this as a 2 horizontal transformation. It can be a 1 horizontal and 1 vertical. So if I were looking, what do I do now? Well, the key is we obviously see that it's wider than what the graph is supposed to be. So if you're dealing with width, whether wider or narrower, you know it's a scale factor. The question is, which way? This way or this way? So if you look at this here, to go from a 4 to a 3, that's not a very, 3/4? 3/4 of 4 is 3. But if you do 3/4 of 1, or 3/4 of 0, you still get 0. It doesn't move over here, okay? Or if you do 3/4 of 1, it comes out further, it doesn't go in closer. So you can just look at a key point and see 4 to 3. First of all, 3/4, usually they work with halves, 2s, 3s. I haven't yet seen 3/4. So the horizontal one's not working. So let's look vertical. Well, here is a 1, and now there's a 4. Oh, that's nice. 1 times 4 is 4. 0 times 4 is still 0. 1 times 4 is 4. All of them work. So what we have is a vertical stretch with a scale factor of 4, multiplying by 4. So like I said, they like using whole numbers, and for fractions so far, like in the book and stuff, seems like to be 1/2 if they use that. but I'm not saying they couldn't use a different fraction. So just check it out, see which way the stretch goes. To me, this one is more intuitive. It's quite easy to see that your vertex needs to move over 2. And to check whether it's a horizontal stretch or a vertical stretch is just a matter of checking out the numbers, how you get from 4 to 3, or how to get from 1 to 4. So what you're looking at specifically is this value or this value. And when you figure out that value, you have to see if it's consistent with your other points. If it's not, then you're on the wrong track. If you can get it to be consistent for your few points that you have, then that's a good indicator you've done it right. So this one I feel is the better solution in this case. And now we are to provide the function itself. So to do that, again, we're going to rely on our algebra and the description we've already used. So we'll compare it with what the book gave, just so that you feel comfortable that I've done it right and not, messed up because I didn't follow the book, right? So here we have a translation of 2. Well, what does this mean? It means that our new value is the old value plus 2. We've added 2 to the original graph, okay? So that means that our original value is the new value minus 2. Now you're like, why am I changing it into terms of x1? Because I have to replace the x1 and make the appropriate x2, okay? So x1 is going to get replaced. This is what did I do to the x1. To the x1, I've added 2. Now I'm at the new x, okay? So what we're doing is replacing pieces here so that we get the correct formula there. For the y value, we have this vertical stretch. So we have y2 is going to be 4 times y1. Now, I don't have to solve for y1, and the reason is because my y2 is already present. It's already by itself. Whereas if you wanted to, you could divide it by 4 and replace it, and you'll have a 1/4 over here. But because you want y2 by itself, you're going to have to multiply the 4 to the other side anyway. So you're going to have to decide which one is easier for you to follow. Like I said, if you want to get the y1 by itself, you can put y1 equals 1/4 of y2. So we have this statement and we have this statement will be put into here. So my y1 is a 1/4 y2, and my x1 is an x2 subscript 2 minus 2, okay? So to solve for y2, we just multiply by 4, which means that needs to go into parentheses, and I get this, and this was squared, so sorry, I need to put this in square. The x1 is replaced with this, but there's still that square up there. And so we have that. This is my now g of x. Okay, so my g of x equals 4 times x minus 2 squared. I don't need the subscripts anymore. It helped me get through it. So I have 4 times x minus 2 squared. Well, if you look at what the book provided for their answer, they gave g of x equals a 2x minus 4 squared. You're like, wow, that's not the same. Let's see. If we factor out, there's a 2 common to both. Get 2, there's x minus 2 squared. Exponents distribute to multiply. So this is the same thing as 2 squared times x minus 2 squared. And 2 squared is 4. So we can take what they give and rearrange it so that it's the same thing that we came up with my description. So the point isn't my method, the book method. The book did right. I just don't want you to not follow these instructions because it could lead you. You'll see later in another example where you can't always do it in whichever order you want. So it's safer for you to follow this. And I also want it to be a little bit more intuitive for you. That means makes a little bit more visual sense. For me, it's kind of hard to jump out to 4. Why would I put the vertex out to 4? You know, that's not really intuitive from my point of view. But what's really important for you is that you see there's more than one way to do it. And that can be a two-sided coin. It can cause confusion because, like I said, the book gave 2 different options and I've provided a third. I gave this algebraic option and the book gave this one. So it can cause you a little confusion. Don't automatically assume that you did it wrong. Step back a little bit and look at it. If you can actually demonstrate that your answer is the same as the book's answer, you're still doing it right, okay? So the downside is it might be confusing having multiple possible answers, but at the same time, it gives you flexibility that you don't always have to see it the same way someone else does. It gives you a little freedom that there is more than one way that you can look at these. There is a matter of perspective that's definitely involved here. So notice if you look at theirs, they obviously have a horizontal translation and they also have a horizontal stretch. Whereas the one that we did here, we had a horizontal and a vertical. So you can have the same set of translations come about more than one way, okay? So use that actually to your advantage. Don't get confused by different possible answers. Just double check to make sure that indeed your answer does fit the answer provided either in the mark scheme or in the book, okay? So let's go on to here, both of these examples, at least the way I did this one, and the previous one was one horizontal and one vertical. Let's look at something different. Okay, here we go with another example. This time we're going to look at 2 horizontal transformations, and it is given to us instead of the graph or instead of the function, it is now given to us strictly as transformations. So we have, this one is obviously a horizontal because it involves the x, the top number. If it was the bottom number, it would be vertical. So this is a horizontal translation, and then also a horizontal stretch with a scale factor 1/2. Now, what I've done is I went ahead and I've graphed our original function. And again, I'm using the quadratic as our parent function, but this could apply really no matter what parent function that maybe they designate for you to use. So again, if we need to make the graph or if we need to make the equation. So if we need to make the graph, what we're going to do is we're going to use these 2, and because it's your x, if we solve for x, we need to undo like whatever's attached to the x. So we need to go in the opposite order of operations, okay? So the opposite order would do addition, subtraction before multiplication if we're going in opposite order. So we need to do this shifting of our, or this translation of our graph 6 units to the left. So if we do that, 1, 2, 3, 4, 5, 6, here we are at -6, and our vertex would be right here. Just going to put a dot. So if this one moves over 6, we have a dot here, and we also have one here at -7. And we would also have one up here at 4, and one over here at 4 as well. So I'm not going to draw it in. I'll just put a little dotted line here. That would be after translating it 6 units to the left. Okay, so just highlighting our key points here, reference points. So now we've done the first one and we're following the advice here. Now we're going to do the scale factor of 1/2. That means we need to multiply each x, because this is horizontal, each x value by 1/2. So if we take half of -6, now we are on -3. And if we, now this is an odd number, this is -5, but here's -4, and here's -8. Okay, so if we take half of -4, that gives us to -2. So -2 will be up here at 4. And our -8 divided by 2 would be at -4. So our final graph, kind of narrow here, goes up like this. So this was our original function, and now this is our new function. Okay, so the old one and the new one, instead of using the subscripts, I just used F and G. And how can we verify this? Is there any way that we can double check this? Well, yeah, there is. Let's go back. Instead of going from description to the graphs, let's go from descriptions and see if we can come up with an algebraic expression or equation. So our new x is going to be the old x, or the original x, minus 6. Because it says to take -6 from our x value, which would mean, and because we are starting with the old function, I want to look for some substitutions here. So what do we substitute in the place of that x1? So our x1 will be y2, or x2 plus 6. Also, horizontally, our x2 is half of x1, meaning our x1 is twice x2. So these two actually need to go together. They're both horizontal transformations. And then the y is y2 just simply equals y1. There's no vertical transformation happening, so we can just directly substitute y2 equals y1, or if you want it the other way, y1 equals y2. Now we have substitutionary values here. So if we want to go back up here, our y1 can just be substituted with y2. Our x1 inside the square here needs to be a combination. This isn't like substitute this into this. They're both transformations occurring. We had to separate them in order for graphing purposes, but these are two different things happening to the same x. So it's not exactly like substituting into multiple equations. So what we want here is for our x1, we need two things to happen to our new x. Our new x needs to be added by 6 and multiplied by 2, and it's being squared. How can we verify this with this? And is there another way of looking at it? Well, first, let's just check if it works. Here we have the point -3, 0. Here we have the point -4, 4. And here we have the point -2, 4. So let's see if that works. If we plug in a -3, we get -6. -6 plus 6 is 0. 0 squared is still 0. We're okay on the first one. If we plug in a -2, -2 times 2 is -4. -4 plus 6 is 2. 2 squared is 4. So we're okay on that one. If we plug in a -4 for the x, 2 times -4 is -8. -8 plus 6 is a -2. -2 squared is again 4. So we can see that our little algebraic connection here put into this would be one way of representing the new equation. It does fit our graph, which we didn't do from the equation, by the way. We did it from the translations themselves. So we went two different pathways and then compared them against each other. Let's check it a third way. What if we factor this? If we factor this, that we can take a 2 out. And then that 2 distributes. So if that 2 distributes, we could call this 2 squared is 4 times x plus 3 squared. And we can keep the little 2 there. We don't really need the subscripts at this point, but it does kind of help us. The subscripts are more helpful up here. At this point, we don't really need them. But let's check. And then instead of having 2 horizontal, what I just did is I converted it to a vertical, because the 4 is outside the function, and a horizontal inside the function. So let's see if that makes sense. And remember, if you have one of each, the order doesn't matter. So we can subtract 3. Remember, you have to do the opposite when it's attached to the x. Subtract 3, and then multiply by 4, and our 1s multiplied by 4 are 4. Or you could have multiplied these ones by 4 and then subtracted 3. Either way. So now we have two different ways of doing the equation, that both of which check against our original graph. Although if you were to describe this, you would have used a different description if you're coming from this. Again, there's flexibility. So try not to allow the flexibility to create confusion. Let it be more of an opportunity for you, realizing that sometimes if you tweak things algebraically, you might make it easier. I think one vertical and one horizontal is a little bit easier than dealing with 2 horizontal or 2 vertical. So you do have options, and it does kind of depend on how they ask the question. That's going to be the real key. You know, if you're forced into a particular direction, then, you know, so be it. But if there's the flexibility, then use that to your advantage. Okay, so we've covered 2 horizontal. Let's move on to the last, and that's 2 vertical. Okay, here's our last example, and we're going to do 2 vertical transformations. Remember, vertical is referring to the y value. So since y is already the subject of this equation, means we're going to do all these calculations in the proper order of operations. Our multiplication comes before add or subtract. So again, I'm using the quadratic as the parent function. So that means this in subscripts, this would be our 1, this would be our 2. Again, it's assuming they provide an original for you, but this one is going to represent the new one. I've also already graphed for us the original, a little bit bigger than this little one, and so that we can see how the transformations take place graphically. So again, we have function, graph, and description. And if you can tie them all together mentally, that's where you start getting that understanding and confidence that we want you to have. So let's start with a little bit of algebra here. Because these are vertical, and you say, how do we know they're vertical just by looking at it? Well, notice there's no parentheses around the x, meaning both of these are outside of the function itself. You see x squared, you see x squared. The 2 is outside, not in parentheses. The -3 is outside, not in parentheses. That means both of those actually belong to the y. They are vertical transformations. So the y, or the x, simply replaced the new x, simply replaced the old x. No transformations. Our y is 2 times the old y value, y is the function itself, minus 3. So actually it kind of looks like the same thing, but we're putting it in terms of the new y compared to the old y. And so here we see our 2 transformations. So this one is a translation, 0, -3, outside the function. This one is our stretch. And of course, it's a vertical stretch with a scale factor of 2. So because we're doing 2 vertical, we want to follow the order of operations. That means we're going to do our scale factor first, and we're going to do the translation second. Okay, so with 2 verticals, we follow the order of operations. So let's see what it looks like on our graph. Well, if we do a scale factor of 2 first, remember we're multiplying the y values, not the x. So this is a 0 times 0 is still 0. Here is a y value of 1 times 2 is now 2. And here is a y value of 4. It now becomes 8. So I need to bring this up a little bit further here. 1, 2, 3, 4, 5, 6, 7, 8. Again, it's a sketch, doesn't have to really be perfect. So we get 2, 8. So we multiplied 4 by 2 and we get 8. This one is a 1 times 2 is now 2, and a 4 times 2 again is 8. So it's a vertical stretch. All these values are being pulled in this upward direction here. And so I'm just going to put a dotted line here because that was our first of 2 translations. Now we're going to do a translation downward. Okay, so we're going to translate the y value. All the y values are going to go down 3. So if you take our vertex down 3, it ends up down here at -3. If we take this, which is at 2, and we go down 3, we're now at -1. And if we take 8 and go down 3, we're now at 5. So 5 would be right in here. And same thing on this side, we go down 3, 1, 2, 3, it's at -1. And we go down 3 and we're at 5. So our black graph here is going to be the final after both translations. So the red one was the original function, the blue one was after the first transformation, and then the black one is after both have been applied to it. Okay, so we see that it was stretched first, then translated. That these are two different vertical, they're both outside of the function itself in front, and then this plus the minus at the end. And so what I want to do now is just demonstrate that if you don't follow this advice, it could get you into trouble. So really quickly, just want to show you how, if you did it out of order, what would happen. So if we did it out of order, what we're going to have is, let's start with our original here, 0, 1, 1, 2, 4. -1, 1, -2 squared is 4. Here's our original. And if we had done the translation first, that would bring us down to -3. And this one down to -3 would be right here. This one down -3, 1, 2, 3 would be right here. And then we would have this one, and this one would be down to right here. So this would be the first step. But then we need to multiply these values by 2, the y values. So our y value is at -3. If we multiply -3 times 2, we now get -6, which is down here. We would have ended up with this. And if we multiply a -2 times 2, we get -4. And if we multiply a 1 times 2, we get 2. It does stretch it. It's not saying that there's not the effect desired. The problem is the outcome. Notice that this graph is not the same as this one. We used the same two translations, but we didn't follow the directions here of either in order when you're dealing with y or opposite order when you're dealing with x. And so it got us into a wrong position. Now, can we verify that this one is correct and that this one is incorrect? Yeah, all you have to do is look at your key points. This is the point 0, x is 0, -3. This is the point 1, -1, and this is the point 2, 5. And if we take these three, this is the point 0, -6, 1, -4, and 2, 2. So let's see which set actually works. If you plug in a 0, 0 squared is 0, times 2 is 0, -3 is -3. You don't get -6. If you plug in a 1, 1 squared is 1, times 2 is 2, 2 minus 3 is -1, not -4. If you plug in a 2, 2 squared is 4, times 2 is 8, minus 3 is 5, not 2. So if you do it in the wrong order, it might, and that's the key, is it might come out wrong. So since you don't know, please follow this, write it down in your notes, and Remember, horizontal deals with the X. If you're solving for X, you have to undo, meaning the opposite order. If you're solving for Y, it's already set up. You just follow the order of operations. Okay, so I hope that helps. I hope you see certain things to avoid. I hope you now have a better understanding of how function, graphs, and descriptions relate together. And I definitely hope that you have successful experience on the new content of the new syllabus for the Pure Maths 1. Again, as always, thank you for joining me in the Zoom room.